Welcome! Today, we'll be tackling an interesting and challenging problem from LeetCode, problem number 1044, longest duplicate substring. In this problem, we'll explore efficient ways to identify the longest repeating substring within a given string. Stick around as we walk through the approaches and concepts that will help us solve this problem. In this problem, you're given a string S consisting of lowercase English letters. The task is to find the longest substring within S that appears at least twice. If no such substring exists, the output should simply be an empty string. The input format is straightforward, it's a single string S. The output is also a string, which is the longest duplicate substring, or an empty string if no duplicates exist. For example, if the input string is banana, the longest duplicate substring is Anna, which appears twice in the string. This example demonstrates that the solution must identify and return the longest substring that repeats within the input string. To understand why the output for S equals banana is Anna, let's break it down. The string banana contains multiple duplicate substrings. For instance, the character A is repeated at indices 1, 3, and 5, the substring Anna appears at indices 1 and 3, and the substring Na appears at indices 2 and 4. Among these, Anna is the longest duplicate substring with a length of 3. In contrast, for the input string ABCD, there are no duplicate substrings since all characters are unique and appear only once. As a result, the output in this case is an empty string, indicating no duplicates were found. Now consider the input string AAAAA. This example highlights how overlapping substrings can contribute to the solution. Here, the substring A appears 5 times, AA appears 4 times, AAA appears 3 times, and AAA appears twice. The longest duplicate substring is AAAA, which has a length of 4. This demonstrates that even when substrings overlap, the solution must correctly identify the longest one among them. Additionally, it's important to note that for larger inputs, the constraints of the problem specify that the length of the string can go up to 100,000, meaning the solution has to be efficient. Brute force methods with quadratic or worse time complexity may not perform well within these constraints. There are several edge cases to consider in this problem. For example, when the input string has a length of 1, such as S equals A, no duplicate substrings are possible, so the output is an empty string. Similarly, if the string contains no repeating characters, like S equals ABCDEF, the output will also be an empty string. On the other hand, if all characters in the string are identical, such as S equals AAAA, the longest duplicate substring will span almost the entire string, resulting in an output of AAA. Another important edge case involves overlapping substrings, as demonstrated by strings like S equals banana. The solution must handle these cases correctly and efficiently to ensure accurate results across a wide range of inputs. To solve the problem of finding the longest duplicate substring in a string, we first considered a brute force approach. The idea here is straightforward: generate all possible substrings of the string, compare them to identify duplicates, and keep track of the longest one. Specifically, we would generate all substrings, use a hash set to check if a substring has been seen before, and update the result when a longer duplicate is found. However, this method is computationally expensive. Generating all substrings alone requires O(n) squared time, and checking for duplicates for each substring adds another O(n), resulting in an overall time complexity of O(n) cubed. This cubic complexity makes the brute force approach impractical for longer strings, as the computation time increases dramatically. While simple, the inefficiency of this method highlights the need for a more optimized solution. To address the inefficiency of the brute force method, we turn to an optimized approach that combines binary search and rolling hash. This method tackles the problem more systematically. Instead of comparing all substrings directly, we use binary search to determine the maximum length of a duplicate substring. For each candidate length, we employ a rolling hash technique to compute hashes of substrings efficiently and check for duplicates. The process unfolds as follows. First, we perform a binary search over possible substring lengths, starting with a range from 1 to n1. For a midpoint length, we compute the rolling hash for all substrings of that length and check for duplicate hashes. If duplicates are found, we adjust the search range to explore longer lengths, otherwise, we focus on shorter lengths. This approach is much faster because the rolling hash allows for efficient substring comparison, and binary search minimizes unnecessary checks. With a rolling hash computation taking O, n, and binary search contributing O, log n, the total time complexity is reduced to O, n log n. However, careful handling of hash collisions and modular arithmetic is crucial for this method to work reliably. Given the limitations of brute force and the efficiency of binary search with rolling hash, the latter was chosen as the preferred strategy. The brute force approach, while conceptually simple, is infeasible for longer strings due to its cubic time complexity. In contrast, the binary search and rolling hash method strikes a balance between performance and implementation complexity. The rolling hash ensures that substring comparisons are efficient, while binary search helps eliminate redundant checks by narrowing down the search space. This approach builds on the critical observation that if a duplicate substring of a certain length exists, then shorter duplicate substrings must also exist, allowing us to prune the search space effectively. The advantages of this strategy include its much faster performance for larger strings and its powerful combination of mathematical optimization and algorithmic efficiency. However, it does come with trade-offs. The rolling hash requires careful implementation to avoid hash collisions, and the overall method is slightly more complex than brute force. Still, the dramatic improvement in performance makes it the ideal choice for solving this problem. In conclusion, the binary search and rolling hash solution emerges as the most efficient and practical method for finding the longest duplicate substring. This approach scales well for larger inputs and achieves a significant reduction in time complexity, dropping from O, n cubed, with brute force to O, n log n. While it may require a more intricate implementation, the performance benefits far outweigh the added complexity. By combining the mathematical efficiency of the rolling hash with the algorithmic optimization of binary search, this solution effectively balances speed and precision, making it the superior choice for tackling the longest duplicate substring problem. Let's continue. Let's continue. Let's continue. Let's continue. Let's continue. Here, we begin by defining a class named solution and implementing the method longestDup substring. The goal of this method is to find the longest duplicate substring within the given string S. To achieve this, we use a helper function called search, which takes the length of the substring we want to check as input. Within the search function, we initialize a set called scene to keep track of hash values of substrings we encounter. We also calculate the initial hash value of the first length characters of the string using a rolling hash technique. The rolling hash helps us efficiently compute hash values for substrings as we slide across the string. Next, we pre-compute a value called Basel, which is used to adjust the hash when removing the effect of the first character in the sliding window. For each subsequent substring of length, we update the hash value dynamically. If the hash value is found in the scene set, it means we've encountered a duplicate substring, and we return the starting index. If no duplicate is found, we return -1. The primary function then initializes some variables, n as the length of the string, nums as a numerical representation of the string, and constant space and modulus for the rolling hash calculations. Finally, we set up a binary search range with left and right pointers to identify the maximum length of the duplicate substring efficiently. Now, the binary search logic continues. Inside the while loop, we calculate the midpoint mid and use the search function to check if there exists a duplicate substring of that length. If the search function returns a valid index, meaning a duplicate was found, we adjust the left pointer to mid +1 to explore longer substrings and update the start variable to store the index of the duplicate substring. If no duplicate is found, we move the right pointer to mid, narrowing the search range. After the binary search completes, we check if we found a valid starting index. If so, we return the substring starting at start with the determined maximum length. If no duplicate substring exists, we simply return an empty string. This approach combines the efficiency of rolling hashes for substring comparison and binary search to minimize the number of checks, resulting in a highly optimized solution. Here, we're implementing the solution for finding the longest duplicate substring using Java. We begin by converting the input string into an array of integers, where each character is mapped to its relative position with respect to a. This helps us work with numerical values instead of characters, which is essential for applying the Rabin-Karp algorithm. Next, we define constants for the base and modulus, which are crucial for calculating hash values. The base is set to 26 because we are working with lowercase English letters, and the modulus is set to 2 raised to the power of 32 to prevent hash values from becoming too large. To determine the optimal length of the duplicate substring, we use a binary search approach. The search range starts with left as 1 and right as the length of the string. We also initialize start to -1 to keep track of the starting index of the substring if it's found. Within the binary search loop, we calculate the midpoint and call the search function to check if a substring of the current length exists. If a valid substring is found, we adjust the search range to explore longer substrings, otherwise, we narrow the range to shorter ones. Once the binary search concludes, we return the substring starting at the recorded index, provided that a duplicate substring was found. If no such substring exists, we return an empty string. Now, let's look at the search function, which implements the Rabin-Karp algorithm to detect duplicate substrings of a given length. First, we compute the hash value of the initial substring of the specified length. This is done by iterating through the first length characters and updating the hash value iteratively using the base and modulus. To handle hash collisions efficiently, we use a set to store the hash values of previously seen substrings. Next, we pre-compute base raised to the power of length modulo modulus, which is used to efficiently update the hash value as we slide the window across the string. This ensures that the hash calculations remain efficient even for longer substrings. With these preparations, we proceed to the sliding window loop, where we calculate the hash value for each subsequent substring by removing the contribution of the first character in the current window and adding the next character in the string. In the sliding window loop, after calculating the hash value for the current substring, we check if this hash value already exists in the set of seen hashes. If it does, this indicates that we've found a duplicate substring, and we return the starting index of this substring. If the hash is not a duplicate, we add it to the set and continue sliding the window. Once we've exhausted all possible substrings of the given length without finding any duplicates, we return -1 to indicate that no duplicate substring exists for this length. This entire process ensures that we efficiently identify duplicate substrings using the Rabin-Karp algorithm, leveraging both hash computation and the sliding window technique. The combination of binary search and Rabin-Karp allows us to find the longest duplicate substring while maintaining optimal performance. To solve the problem of finding the longest duplicate substring, we start by converting the input string banana into a numeric representation where each character is mapped to a number based on its position in the alphabet. For example, A becomes 0, B becomes 1, and so on. This gives us the array 1, 0, 13, 0, 13, 0. Next, we define two constants, the base, which is 26 representing the number of letters in the alphabet, and the modulus, which is set to a large value of 2 to the power of 32. These constants will help us efficiently compute hashes using the rolling hash technique. We then initialize the bounds for binary search with left set to 1 and right set to the length of the string, which is 6. The first binary search iteration begins by calculating the midpoint, mid, as 3. We then call the search function with mid equals 3, which computes the hash for the first 3 characters, ban. Using the rolling hash technique, we calculate hashes for the subsequent substrings, such as Anna and Nan, while storing each hash in a set. When we encounter a hash for Anna that already exists in the set, we identify this as a duplicate substring starting at index 1. Based on this result, we adjust our binary search bounds by setting left to 4 and storing the starting index of this potential result as 1. Next, we proceed with the second iteration of the binary search by recalculating the midpoint as 5. The search function is called again, this time with mid equals 5. We start by computing the hash for the first 5 characters, banan. Using the rolling hash technique, we calculate hashes for the remaining substring, anana, but no duplicate hashes are found. Consequently, the search function returns -1 to indicate no duplicates of length 5. As a result, we update our binary search bounds by setting right to 5. At this point, the binary search terminates when left equals right, and the longest duplicate substring is determined by extracting the substring starting at index 1 with a length of left 1, which is 3. This gives us the substring Anna. Now, consider a different input, ABCD. We begin by converting the string into its numeric representation as 0, 1, 2, 3, and initializing the same constants, base equals 26 and modulus equals 42949679296. The binary search bounds are set with left equals 1 and right equals 4, reflecting the length of the string. For the first binary search iteration, we calculate the midpoint, mid, as 2. The search function computes the hash for the first two characters, UB, and adds it to a set. Using the rolling hash, we check the hashes for the substrings BC and CD, but no duplicates are found. Thus, the search function returns -1, indicating no duplicate substrings of length 2. Based on this result, we adjust the binary search bounds by setting right to 2. In the second iteration of binary search, we calculate the new midpoint as 1. The search function is called with mid equals 1, where it computes the hash for the first character, and adds it to a set. Using the rolling hash, we compute hashes for the remaining characters B, C, and D, but no duplicates are found. As a result, the search function returns -1 once again. The binary search bounds are updated by setting right to 1. At this point, the binary search terminates, and since no duplicates were found throughout the process, the function returns an empty string as the result. For the input AAA, we convert the string into its numeric representation as 0, 0, 0, 0, 0. The constants remain the same, with base equals 26 and modulus equals 42949679296, and we initialize left equals 1 and right equals 5. In the first binary search iteration, the midpoint is calculated as 3. The search function computes the hash for the first three characters, AAA, and adds it to a set. Using the rolling hash, the function calculates hashes for the remaining substrings, all of which are also AAA. Since a duplicate is found, the search function returns the starting index 1. Based on this result, we update left to 4 and store the starting index of the potential result as 1. In the second iteration, mid is recalculated as 4. The search function computes the hash for the first 4 characters, AAAA, and adds it to a set. Using the rolling hash, the remaining substring hash matches, indicating another duplicate. The search function again returns the starting index 1, so we update left to 5 and store the starting index as 1. Finally, the binary search terminates when left equals right, which is 5. The longest duplicate substring is determined by extracting the substring starting at index 1 with a length of left 1, which is 4. This gives us the substring AAAA, which is the result for the input AAAA. Here, we analyze the time complexity of the solution, which involves a combination of binary search and rolling hash. First, binary search is applied to determine the length of the duplicate substring. Since the search range spans from 1 to the length of the input string, n, the number of iterations required is proportional to log n. Next, we have the rolling hash computation within the search function. For a given substring length, the hash of the first substring takes O, length, to compute. Subsequent hashes are updated in constant time using a sliding window approach. Since the total number of substrings of a specific length is approximately n, the overall cost for rolling hash computation at each binary search step is O, n. Together, these operations lay the foundation for understanding the time complexity of the algorithm. Now, we consider the set operations performed within the rolling hash computation. For each substring, its hash is stored in a set, which allows us to check for duplicates efficiently. Both the insertion and lookup operations in a set average to O(1) for each substring. With n substrings of a given length, the total cost of these set operations is O(n). When we combine the rolling hash computation and set operations, the dominant cost for each binary search iteration becomes O(n). Since binary search involves O log n iterations, the total time complexity of the algorithm is O(n log n). This efficiency highlights the power of combining binary search with rolling hash for substring matching. Turning to space complexity, the solution requires storage for certain data structures and variables. A set is used to store the hashes of substrings. In the worst case, this set could contain up to n unique hashes, resulting in O(n) space. Additionally, the nums list is used to store the integer representation of the input string, which also requires O(n) space. Beyond this, auxiliary variables such as #_value, Basel, and modulus each consume constant space, contributing O(1) in total. Thus, the overall space complexity of the algorithm is O(n), dominated by the set and the nums list. To better appreciate the efficiency of this solution, let's compare it to the brute force approach. The naive method involves generating all possible substrings of the input, which results in n squared substrings. Each substring comparison takes n time, leading to a staggering time complexity of n cubed. Additionally, storing all substrings would require n squared space. In contrast, the optimized solution reduces time complexity to n asterisk log n, and space complexity to n. This improvement is achieved by leveraging rolling hash to avoid redundant substring comparisons and binary search to narrow the search space. Whether in the best or worst case, the algorithm consistently operates within n asterisk log n, making it significantly more efficient. Finally, we can mathematically validate the big O analysis of this algorithm. For each iteration of binary search, the rolling hash computation processes all substrings of a given length, taking n time. Since binary search performs log n iterations, the combined time complexity is n asterisk log n. On the space side, the set used for hash storage and the nums list collectively require n space, while auxiliary variables contribute only a constant amount. This makes the overall space complexity n. By avoiding the inefficiencies of the brute force approach, this algorithm is well suited for handling large input sizes, such as strings with lengths up to 10 to the power of 5, ensuring scalability and performance. When tackling this problem, one common pitfall is overlooking edge cases. For instance, you might miss scenarios like empty strings, strings where all characters are unique, or highly repetitive patterns such as AAAA. Neglecting these can lead to runtime errors or incorrect outputs because your solution may not generalize well. Another frequent mistake is using a brute force approach to check all substring pairs. While conceptually straightforward, this results in an n cubed complexity, which is far too slow for large inputs like n equals 10,000. Misusing rolling hash is another issue. This typically happens when hash functions are not implemented correctly, leading to hash collisions or errors in modulo arithmetic. These issues can cause false positives or incorrect hash values, undermining the solution's accuracy. Lastly, errors in binary search logic, such as incorrectly defining boundaries or improper midpoint updates, can result in infinite loops or failure to identify the correct substring length. These mistakes highlight the importance of precision in both logic and implementation. Another common error is not validating duplicate substrings properly. Matching hash values alone doesn't guarantee that the substrings are identical, as different substrings can sometimes produce the same hash. Without proper verification, this can lead to incorrect results. Now, from an interview perspective, it's important to recognize the patterns in this problem. Specifically, the combination of binary search with hashing is a common strategy for substring search problems, so understanding this approach is key. Interviewers also value your ability to weigh trade-offs. For example, while brute force is simple, it's inefficient, whereas methods like rolling hash or suffix arrays are faster but more complex to implement. Optimization is another focus. You should be able to explain how you'd start with a naive approach, then refine it for better performance. Finally, understanding the spacetime trade-offs is crucial. For instance, storing hashes or suffix arrays can improve speed but also increases memory usage. Be prepared to articulate how these factors impact the overall solution. This problem also connects to several related challenges that are worth exploring. For example, in LeetCode Problem 5, Longest Palindromic Substring, you work on substring searches using dynamic programming or expand around center techniques. While the context is different, the substring manipulation concepts are similar. Then, of course, there's LeetCode 1044, which is the problem we're discussing. It directly involves binary search and hashing strategies, making it the centerpiece of this discussion. LeetCode Problem 718, Maximum Length of Repeated Subarray, introduces similar concepts, focusing on efficient substring comparison and optimization. Lastly, LeetCode Problem 1062, Longest Repeating Substring, is a variation that centers on identifying repeated patterns within a string. By understanding these related problems, you can deepen your grasp of substring search techniques and become more versatile in handling similar challenges. There are also alternative approaches to solving this problem, each with its own strengths and trade-offs. One option is using a suffix array. This involves constructing the array and leveraging the longest common prefix, or LCP, to identify the longest duplicate substring. While efficient with an O and log n complexity, it requires a strong understanding of suffix arrays, which can make it challenging for some. Another method is the rolling hash with Rabenkarp. This technique uses a hash function to compare substrings, combined with binary search for added efficiency. It's fast and memory efficient, but you need to implement it carefully to avoid hash collisions, which can compromise accuracy. Finally, there's the dynamic programming approach. Here, you use a DP table to track substring matches. While it's relatively easier to understand, it's less efficient, as it comes with O, n squared, space and time complexity. Each method has its place, and the best choice often depends on the constraints and requirements of the problem you're solving. Thank you for joining us today. We hope this explanation helped you understand the problem and the solutions better. Remember, mastering these techniques will significantly boost your problem-solving skills. Don't forget to subscribe for more insightful tutorials, and we'll see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!